Okay, good morning, folks. It's probably about time to get started. So I've got a couple of logistics updates to discuss with you, nothing too groundbreaking. So first off, thank you everyone who submitted the exam regrades. That was very useful as an exercise, I think. I got those graded and returned over the weekend. People generally did very well, and I was very pleased to see the people who made the effort to go back and go through these kind of problems one more time for some credit back on the exam. I think that definitely helped people out. I haven't done the detailed analysis on the grades yet after having done the regrade submissions, but one thing that I do know is that the average shifted significantly. The average before the regrade was a 75 with a very wide standard deviation. And then after including the points back from the regrade, that lifted this average up to an 81, which coincidentally is also exactly the average on the regrade itself. But overall, I was very pleased with this. This number includes both a few people who didn't need the extra points, but did the regrade for the extra practice. And I applaud you for doing so. It also includes a number of people who lifted their grade by a letter grade or more. So I think this is very helpful. Okay, so that was the exam regrade. Homework 6 has been posted. I put that up the end of last week. That is due this Friday. That's another standard length homework assignment on perturbation theory, time-dependent perturbation theory. A couple of points that I want to emphasize on this. So let me share screen for a moment. All right, are you guys seeing this?
Yeah.
Okay, good. So here is homework 6. It is due this Friday. We're back to standard homework protocols where I'm not going to penalize you if you don't get it turned in on time, but sooner or later the bill is going to come due. So if you get behind on submitting the homeworks, it's going to come back to bite you, but please get this in as soon as possible. So, so one thing that you'll notice when you take a look at this is that I have added 2 conceptual questions. So problem 1 is 2 conceptual questions and 2 short calculations. These calculations are maybe a little bit longer than I would ask on an exam format, but they are shorter than what I would have given for a normal homework problem. These are sort of direct applications of the formulas we've derived in class. So question 1 is worth a total of 15 points rather than 10, including the 2 conceptual questions. So it takes a little bit of thought to come up with a good conceptual question for something like time-dependent perturbation theory, but I think I'm pretty happy with these. So I tried to make sure that these align with the key concepts that I emphasized before. So take a look at those. One other thing that I wanted to mention and raise with you guys specifically, as we saw last time and we'll review today, when you do time-dependent perturbation theory, you very naturally end up doing Fourier transforms because time-dependent perturbation theory is naturally described in terms of the absorption of plane waves, which deliver a finite amount of energy to the system. So if you have a time-dependent pulse, something which is Gaussian, or something in this case which is Lorentzian, you end up essentially Fourier transforming that time dependence. There's lots of issues that come up when you Fourier transform things. In this particular example, the Fourier transform of the Lorentzian is most easily done using contour integration from complex analysis. When I put this problem together, I was not sure how much guidance I should give you on how to do that. So I asked Dr. Engelhardt, and he said everybody who took his math methods class in the fall should be exquisitely familiar with Fourier transforms by contour integration. So I wanted to ask you guys, how comfortable are you with this? Do you need me to provide some extra guidance on how to do the contour integration, or can you just take it and run with it? What's your level of comfort with that subject?
I would say mild to low. We did go over it. That does not mean it was not complex.
Right. Yeah,
at least from my point of view.
Very different topics. So for instance, the kind of integral that you're going to need to perform is something that looks like this. You'll have an integral dt. It's a Fourier transform, so you'll have e to the minus I omega t. And your integram will have something like t plus ix t minus iy. And to do this thing, you're going to need to identify what are the poles of this denominator. Where are they in the complex plane? Are they above or are they below? And you're going to need to figure out, how do I close the contour, above or below the real axis?
Okay, yeah, that's pretty familiar.
Starting to ring some bells? Okay, I'm not sure what the best way to give you that kind of extra guidance is. Of course, if anyone has specific questions, you are welcome to send me an email, come to my office, and we can discuss. Maybe I will add up a page of supplementary notes on this for people who just need to quickly refresh themselves. But based on what Dr. Engelhardt told me, I just put the question on the homework as is. But I was a little bit concerned because this hasn't come up in our class yet. It will eventually come up again in the future, though. So this is something to make sure that you're okay with. Okay, let's see. I think I have something in chat here. Some notes with an example would be very useful. Yes, I can certainly do that. Okay, so that's really only an issue for this part C, this first calculation, where the thing that you are Fourier transforming is this Lorentzian profile. The other example is another Gaussian profile. This is the same Fourier transform we did in class. So this one is done by completing the square. You'll note that the answer looks familiar, this e to the minus 1/2 omega squared tau squared. Which means I need to fix what's on the board. Yeah, so this is very similar to the example that we did in class, except this is now for the one-dimensional square well, as opposed to the harmonic oscillator. So that ends up, you have to do an integral over x, and you get lots of different coefficients depending on n, but conceptually it's not any harder than the example we did in class. So question number 2, I really struggled finding good problems to give you on time-dependent perturbation theory that were not scattering theory. So to make a long story short, what I did was I pulled a problem from the comprehensive exam. So this is problem 4 from the 2019 comprehensive exam, which actually does not have anything to do with time-dependent perturbation theory. When I started looking at it, I said, oh, this form looks like what we discussed in class, so maybe this is a good problem to do. It turns out that it has almost nothing to do with time-dependent perturbation theory, but I thought it was good practice anyway. So the first several parts of this problem are sort of reminding you about the starting point for a problem like this. This is the actual question that was on the exam. And then this numerical calculation was a subpart of that question. And all I did was I added on a little piece at the end that applied time-dependent perturbation theory to this problem. But this is mostly just a review of other things we've already done and an opportunity to practice some more about problems on the comprehensive exam. I think that's it for homework number 6. Do you guys have questions, comments, or concerns for me? Okay. If not, so like I said, I spent the weekend getting caught up on regrade submissions, so I still have not gotten homework 4 back to you. I'll get that to you as soon as I can, but like I said, I'm going to prioritize the new stuff rather than returning back homeworks. Okay, so if there's nothing else, then let's dive on into physics for today. And let me fix this factor of 2 before that has a chance to propagate. Okay, so last time we were discussing time-dependent perturbation theory. The cornerstone of all of the results of time-dependent perturbation theory is the dressed propagator. This thing gives you the time evolution from initial time t0 to final time t under the presence of an interacting Hamiltonian that is both the bare Hamiltonian and a perturbation, which is time-dependent. And the answer looks very familiar and it's very intuitive. When you expand this propagator in perturbation theory, the 0th order in perturbation theory answer is free particle propagation. This is the time dependence of the unperturbed Hamiltonian U0. The first correction from perturbation theory contains exactly 1 insertion of the perturbing Hamiltonian. You're integrating this thing over all times between t0 and t, and that 1 perturbation could have happened at any time t prime in between. And so very intuitively, the expression is free propagation from the initial time t0 to t prime. At t prime, you get hit by the perturbation. And then again, you have free propagation from t prime to t. At higher orders in perturbation theory, you continue the series and you have all time-ordered insertions of 2 or 3 or n number of interacting Hamiltonians. One thing that we did with this was we used it to calculate transition rates. This goes by the name of Fermi's golden rule, which is one of the most important formulas that we derive in time-dependent perturbation theory. This tells you about the transition rate, probability per unit time, that is flowing from some initial state to some final state as a result of this perturbation. The answer is something really simple and again, very intuitive. The transition rate goes like the amplitude squared that's driving the transition times 2 pi times an energy conserving delta function. The idea was that anytime you have an oscillating perturbation, something with e to the minus I omega t, that perturbation is delivering energy to your system. So if the frequency of the perturbation is omega, that perturbation is delivering energy h bar omega that adds from the initial energy plus h bar omega to give you the final energy. And only transitions that conserve energy overall will survive as t goes to infinity. Virtual quantum fluctuations can happen in between, but the only long-lived infinite future answers can come from energy-conserving transitions. So the basic ingredients are amplitude squared, energy-conserving delta function, and the delta function comes with a 2 pi. Usually delta functions come with 2 pi's because of Fourier transforms. And there's a 1 over h bar for dimensions that takes energy into time, since this is probability per unit time. So these were the main cornerstone results. We used this formula to calculate transition amplitudes and therefore transition probabilities. And we derived and applied this formula to calculate transition rates. The last thing that we discussed last time was a straightforward example of the Gaussian pulse. This Gaussian time profile is the same as problem D on the homework assignment. Actually, the entire perturbation is the same as problem D on the homework assignment, except this operator in the homework is being applied to the square well. In class, we applied it to the harmonic oscillator. The idea was when you plug this formula into the time-dependent propagator and you ask for the probability to transition, effectively what you get is a Fourier transform of this time-dependent profile. So if the time-dependent perturbation came in as a Gaussian in time, effectively the physics is you Fourier decompose that time-dependent profile into a sum of frequencies. And each of those frequencies tries to match up with a transition in the system. And in this example, this operator drove a transition from the ground state to the first excited state, and it picked out just the one particular frequency in that frequency spectrum that could match that transition. So these ingredients are general. Time-dependent profile gets Fourier decomposed, and those frequencies get matched to transition levels inside the system. So the final answer that we got was, in this expression, the probability to transfer from the ground state 0 to any excited state n was 0 except for the first excited state, only 0 to 1. That transition had an overall coefficient. It was proportional to the width tau squared of that time-dependent pulse. And it had the Gaussian factor e to the minus 1/2 omega squared tau squared. So these are things that will show back up on the homework when you again have a profile of this type and you are doing the Fourier transform of it. Any questions on the big picture stuff that we talked about last time? Dressed propagator in a time-dependent picture, Fermi's golden rule, what that looks like in terms of a Fourier decomposition of a time-dependent pulse. Okay, so if not, the next thing that I want to talk about is two different limits of time-dependent perturbation theory. So when we take this expression for the transition amplitude and we write it down, we find that the time dependence contains two time-dependent factors. So if I have something like the absolute value of the transition amplitude is a function of time, dress propagator from T0 to T, final state, initial state. This thing was absolute value of 1 over h bar integral dt prime from T0 to T. We have the transition amplitude final perturbation of T prime initial, And then we had the phase factor e to the plus I over h bar, E final minus E initial, E final minus E initial times T prime. And so this was the answer in first order in perturbation theory. What I want to point out here is that there's two different time scales that are potentially competing with each other in this formula. There's whatever the time dependence of the perturbation is, and then there's the time dependence up here in this phase. We talked about how the results for time-independent perturbation theory are describing a time scale, that this energy difference, delta E is E final minus E initial, that energy denominator that shows up in your perturbation theory, where it has something like final perturbation initial over E initial minus E final, that energy denominator is really talking about a time scale. That time scale, delta T, is H bar over delta E. That's exactly what goes into this phase factor. So that one is, put an absolute value around this because it doesn't matter whether it's positive or negative, E final minus E initial. This is the time scale which is associated with the transition. This is the time that it would take to go from initial state I to final state F. And that depends on how different the levels are. This one, however, contains whatever time dependence was in your pulse. So this is the time dependence of the perturbation. So in this example of the Gaussian pulse, there was a characteristic time tau that controlled the width of that Gaussian pulse. So in general, there are two time scales here. If the two time scales are comparable to each other, then you just have to do the integral. There's no simplification. But there are two limits of this where the time scales are very separated, when this expression simplifies. Those two limits are the case when either the time dependence of the perturbation is very slow compared to the time dependence of the transition. That's called the adiabatic approximation. Or you have the case where the time dependence of the Hamiltonian is very fast compared to the time dependence of the transition. That's called the sudden perturbation in the language that Shankar uses. So the point of this is there are two time scales. The time scales are the time scale of the perturbation For this discussion, I will refer to it as tau the same way as we did for the Gaussian pulse. And then there's the time scale of the transition or of the quantum fluctuation. So that is delta t, which is h bar over E final minus E initial. Absolute value, because that thing could be positive or negative. So in the limit, when the time dependence is very short, we can simplify that integral. So this is what Shankar refers to as the sudden perturbation. So this is the case when the time scale of the perturbation is very, very short compared to the time scale of the quantum transition. So you can think of this as the case of a perturbation that suddenly switches on almost instantaneously. So the physics of this is that the state does not have time to transition. If this is how fast the perturbation happens, and this is how much time it takes to jump to a different state, then it's intuitively clear that if this perturbation happens very quickly and it does not have time to jump to a different state, then your system will stay in the same state it was originally. So the physics is system does not have time to transition. and it remains in the same quantum state it began in. So for example, imagine that you have a perturbation h1 of t, which is some time independent operator times a theta function of time. This is a step function. So my perturbation is off for t less than 0. So this is my function of time. The perturbation is off below t equals 0, and then all of a sudden it turns on instantaneously at t equals 0. What does that do to my transition amplitude? So I have 1 over h bar integral dt prime from t naught to t. Let's see. So I have final Hamiltonian as a function of t prime, initial times the phase factor e to the plus I over h bar, e final minus e initial times t prime. If this thing is a theta function, then I pull out the time independent part, and my integral only goes from 0 to t. So I have 1 over h bar, final Hamiltonian, which is time independent, and now I'm integrating dt prime from t equals 0 to t. And then this has come outside completely, e to the I over h bar, e final minus e initial times t prime. So if I ask myself, what is the state of the system right after t equals 0? What is the state of my system right here? Right after the perturbation hits? Then I'm going to take the limit as t goes to 0 of this expression. What is the state right after? In this expression, t only shows up in one place, and that is here in the upper limit of integration. So if I take the limit when t goes to 0, what I get is integral from 0 to 0 dt prime e to the I over h bar e final minus e initial t prime. It doesn't even matter what everything else is, because there is 0 width to this integral. Essentially, the amount of time goes to 0, exactly as you would think intuitively. The system does not have any time yet to respond to the sudden perturbation. So this theta function is the extreme case when the perturbation takes 0 amount of time. It's also true if it takes a small amount of time. So you could smooth out that theta function and make it a finite width transition, but the picture is still the same. So one important limit that you need to understand physically is this sudden perturbation case. So one example that Shankar gives is if you have a hydrogen state and then all of a sudden the nucleus beta decays. Your electron is sitting there minding its own business in the ground state, and then instantly the Hamiltonian changes on it. It does not have time to respond, but suddenly it finds that it's no longer in an eigenstate because the potential changed. So we will do some more examples of this. Any questions on the sudden perturbation limits?
Just to be clear, right in front of the integral, is that a 1 over h bar or I over h bar?
So I've written it as 1 over h bar. Since I've taken the absolute value, I didn't care about the I. It started off before we took the absolute value. All right, so the opposite limit is the adiabatic limit, the case when the perturbation is very slow. So this is the case when the time scale of the perturbation is much longer than the time scale of the transition. So in this case, if I have a time-dependent expression, transition amplitude T, T naught, I, absolute value, there is an I, but I don't care because it's inside an absolute value, 1 over h bar dt prime from T naught to T, final perturbation, initial e to the I over h bar, e final minus e initial T prime. So in this assumption, the time dependence here inside the Hamiltonian is very slow compared to the time dependence here. That means that this expression is roughly constant over that integration range. So this is approximately constant over this time. So what I can do is I can approximate this as just the Hamiltonian at time t. Final h1 of t initial, and then I pull it outside the integral. Final perturbation of t initial, and then I get just the integral of the phase. T naught to t, e to the I over h bar, e final minus e initial times t prime. This integral I can do immediately, and the answer looks familiar. I had 1 over h bar here. When I integrate this thing, final Hamiltonian of t initial, I get the energy denominator downstairs, I over h bar, e final minus e initial, and then I have a set of complex phases, e to the plus I over h bar, e final minus e initial t, minus e to the plus I over h bar, e final minus e initial t naught. So absolute value means I don't care about the factor of I, h bar cancels h bar, and I get something that looks like time-independent perturbation theory. Hamiltonian of t initial over e initial minus e final, the energy denominator times some phases. The thing that I want to point out is that this object here is exactly the same one that shows up in time-independent perturbation theory. We said things like, oh, the energy shift of state n at first order is the expectation value of the perturbation, and so on. The only difference is this thing is not really time independent, it's just slowly time dependent. So you end up with something that is time dependent, but you don't have the full complication of the time-dependent perturbation theory. These scales don't talk to each other if they're well separated. So in other words, this looks like you get a time-dependent eigenstate. So it looks like, oh, my state n is just slowly varying as a function of time. The energy of that state is just slowly varying as a function of time. So the physical picture here is, if the perturbation is so slow, then the system always has time to relax back down to the state that it began in. So if I start off in the ground state and I very, very slowly change the potential, then at every moment in time, the system has plenty of time to relax back down. I never move it so fast that I excite a transition. And it always stays in the same quantum state of the Hamiltonian, which is evolving as a function of time. So this means that the system always relaxes to the corresponding eigenstate the time-dependent Hamiltonian. So let me illustrate this visually. This is actually something that we talked about last semester without the framework of time-dependent perturbation theory behind it. You guys did a homework assignment for the square well, where we talked about what happens if I change the width of the square well, and I change it very fast or I change it very slow. So the example we did before was expanding a square well. If we started off with a system in a square well of length L, and it starts off in the ground state. So it starts off in the state size 0, and I'll put a little L up here to mean that this is the ground state 0 of a well of size L. So the sudden case, if I take this width and I suddenly double it before the system has a time to respond, the wave function looks identical. So here's 0, here's L, here's 2L. Suddenly I double the well. If I change the potential very fast, the wave function has not had time to respond. It is still in the state size 0 of L, and it hasn't realized yet that the potential has changed. So this is the sudden case. It is still in the exact same quantum state that it started off with. It has not responded to the change in potential yet. Now, the difference is, of course, this state was a perfectly good, stable eigenstate of this well. That same state is not a perfectly good, stable eigenstate of the new well. So right after the perturbation, it's going to fall apart. And so the problem that you guys did before was you took this and you expanded this old wave function in terms of the new wave functions that depended on length 2L. And you found that this state was a superposition of multiple waves in the new well. The other case is if you did it very slowly and adiabatically. So now if I take this and I go from a length L to say L plus epsilon, 0L, L plus epsilon, just a little bit, and I do it very slowly, my old wave function would have ended here. But if I do it very slowly, then the wave function has enough time to expand and match the new well. And if I keep doing this slowly enough, then eventually I can allow it to fill up the entire well from 0 to 2L and stay in the ground state. So this system ends up in the state size 0 of 2L. It is the ground state of the new Hamiltonian. Started off in the ground state of the old Hamiltonian. You do it slowly enough, it stays in the ground state the whole time. It's in the ground state of this thing, it's in the ground state of that thing, it's always in the ground state everywhere as a function of time. As opposed to the sudden case when it started off in the ground state of the first thing and it never changed. And now suddenly it wakes up one day and says, oh my God, I'm not in the right Hamiltonian anymore. And then it has to react. Is this picture clear? The physical intuition and the physical difference between changing a perturbation fast so that it cannot respond and changing a perturbation slow so that it always relaxes. Clear?
Yeah.
Yes. Okay. The thing that I want to emphasize is that this difference comes from a competition of two time scales. So when you ask yourself, is it fast or is it slow? That's not a wishy-washy question. You are comparing two numerical values of time scales. So this is controlled by the time scales tau, whatever is the time scale of the perturbation. And you're comparing that to the time scale of the transition, delta t, which is h bar divided by delta e. So this is related to the transition energy. So when you think about it in terms of Fourier analysis, we said any kind of time dependence gets broken up into frequencies. And every frequency means you're putting energy into the system. If I had a time-independent Hamiltonian, that would be omega equals 0. There's no frequency, so I'm not adding in any energy to the system. The trick is, if you want to expand it adiabatically, it's got to be so slow that it's almost constant, that its omega is very, very low, so that even though when I change the system, I add a little bit of energy, if I add just a tiny amount of energy that's way less than the energy that it would take to actually excite a transition, then that corresponds to my time scale being very slow here. So you can think about this in terms of energy, right? Like, adiabatic would mean that your h bar omega of the transition is much less than delta E. So it cannot excite a transition. I'm making a point to emphasize this here because there's a very important example where this falls apart. And that's the case when delta E is 0 or delta E is close to 0. So if you have degenerate states, or even almost degenerate states, if delta E goes to 0, right, that means I've got lots of levels that are sitting on top of each other or almost on top of each other. And then I cannot ever change my system slow enough. Like, no matter how long a wavelength I put in, no matter how low my omega, there's always a state there, however close you want, and I can always cause a transition. So for the case when you have degenerate states or very closely packed states, it is impossible to change the system adiabatically. So it cannot change adiabatically. Or in other words, you cannot avoid causing a transition by going slow enough. H bar omega goes to 0. Does that make sense? Does that make sense why if this why if the energy levels are close together in energy, adiabatic approximation is out the window? Yes, is this okay?
I guess I'm just confused as to how it would correlate to like the picture right behind you. Because if you go slow enough, it looks like a ground state will have time to react, in the picture in the square well.
Yeah, so maybe let me try and draw another picture beside it. I think maybe I can put something over here. So the idea before was, if I have a system like a harmonic oscillator where I've got a nice finite gap between my states. So I've got state 0 here, I've got state 1 there, and the amount of energy in between these is h bar omega. So the whole idea is if I had a perturbation, right, so let's say it would take a frequency like this to actually drive the transition. This is the magic value omega where I can cause something in the ground state to jump up to the excited state. Adiabatic approximation means I'm going to get as far away from that as possible. I want to send a very long wavelength perturbation in here. Something whose frequency is so low that I will not cause this. So the whole idea is I need the energy of my perturbation, which means the frequency of the perturbation, to be very, very low, much, much lower than the actual gap between the states. So the time scale is equivalent to an energy difference. And so whatever the difference is between my energies is, if my frequency h bar omega is much smaller than that, then I do not excite the transition. That's what adiabatic means. It's another way of saying the same thing. But this requires that there be a nice healthy gap between my states so that I can say, oh, I'm going to send something in with way low energy compared to that. And then I will definitely not cause a transition. But if my states are extremely close together, then I can't avoid the problem. I can't send something with low enough energy or low enough frequency or slow enough perturbation to avoid that problem.
Okay, that makes sense.
More sense? Okay. Yeah. So the idea is energy difference is what sets the time scale, and adiabatic means you're sending in something with energy that is infinitesimal compared to that, so that you do not cause a transition. But it breaks down if the levels themselves are not well spaced. Okay. So the last thing that I wanted to say about general discussion of time-dependent perturbation theory was to revisit an old problem. So previously we had dealt with the example of paramagnetic resonance. So we had the case where we had a magnetic field, B naught, which was pointing along the z-axis, and then we had an external sort of transverse rotating field B, I'll call it, say, B perp, which is rotating around in the xy plane. And we were looking at the impact of this on a spin. You had some spin vector, let's say, causing magnetic moment mu, and this spin is precessing counterclockwise around that external magnetic field. And then when you turn on that rotating magnetic field, some funny things happen. We cause that spin to sort of deflect down in the, let's say, the ZR plane. So it's tilting down away from the z-axis as a function of time. So this was a problem that you guys did on homework 2. So we can discuss this same problem now in the language of time-dependent perturbation theory and understand it again in a different way. So before I turned on the perturbation, my Hamiltonian contained only the magnetic field B naught along the z-axis. So I had something like minus G gamma B naught SZ. This is my bare Hamiltonian. And it's convenient to write this as the precession frequency omega naught. So this is minus omega naught SC. And so this system had two states. So when I look at the eigenstates of this, I had, let's say, the ground state. Here, maybe let me write it this way. H0 on the spin up state has energy minus H bar over 2 omega naught. So this spin up state is the ground state, where the spin is aligned with the magnetic field. And this Hamiltonian acting on the spin down state gave me plus H bar over 2 omega naught. This is the excited state. The one that is aligned with B. This is the one that is anti-aligned with B. So what is the effect of turning on that rotating magnetic field? We can describe that effect using time-dependent perturbation theory. So in the problem, the time dependence came in from this transverse magnetic field. I'll call it B perp as a function of t, which we said was some magnitude B cosine omega t I minus sine omega t j. And so, of course, this leads to a time-dependent Hamiltonian, the perturbation h1 of t, which is minus G gamma spin dot B. In this case, B perp of T is the perturbation. So this gives me minus G gamma B, and then I have H bar over 2 cosine omega T sigma X minus sine omega T sigma Y. I can write this very simply in terms of Fermi's golden rule, because I can convert these sines and cosines into Fourier factors. This is minus g gamma b h bar over 2. Cosine is e to the I omega t plus e to the minus I omega t divided by 2. Sigma x minus sine is e to the I omega t minus e to the minus I omega t over 2i. Sigma y. All right, so I can clean this up. If I collect the terms that have e to the plus I omega t, I have an overall minus g gamma b h bar over 2. E to the I omega t comes with, let's see, so let me pull out the overall factor of 1/2, so let's make this a 1/4. So I have sigma x minus 1 over I, which is plus I, sigma y, plus e to the minus I omega t. That one had sigma x minus I sigma y. Now this is starting to look familiar. I've split up this Hamiltonian into one piece, which is a plane wave, e to the I omega t, another one with e to the minus I omega t. This combination of operators looks familiar to me. If I absorb the h bar over 2, this becomes the raising and lowering operator, s plus and s minus. G gamma b over 2, and I put this back in and I get to the I omega t s plus e to the minus I omega t s minus. Yes. So this oscillating magnetic field, you can see now very clearly, is sending in one kind of frequency that wants to flip the spin up, raise the spin, a different kind of frequency that wants to raise the spin or lower the spin down. So let's calculate what the transition amplitude and the transition probability are as a function of time. So using Fermi's golden rule, let's calculate the transition rate from the ground state, which was spin up, to the excited state, which is spin down. So this is R minus plus, starting in plus, going to minus. This is 2 pi over h bar. The final state is spin down, perturbation. Initial state is spin up squared times delta function of the energy of the excited state. So let's call this E minus E plus minus h bar omega. I have to say plus or minus h bar omega because we have 2 different frequencies here. Let me expand this out and it'll be a little bit clearer. So there are 2 terms to this thing. One of them comes in with e to the minus I omega t. That was the case that we wrote down Fermi's golden rule for. So in this case, I have R minus plus is 2 pi over h bar. The first piece is, I have matrix element, let's see, I'm going to minus from minus g gamma b over 2. The first term is, let's say, s plus, acting on plus squared. And this one would come with the delta function, which is energy final, which is the energy of the minus state, minus energy of the plus state, plus h bar omega. This one is plus h bar omega because the frequency here was plus I omega t. The second transition, minus g gamma b over 2s minus on plus, delta function e minus minus e plus minus h bar omega. So I wrote two terms for Fermi-Golden rule because I had two different perturbations. This one with e to the minus I omega t, this one with e to the plus I omega t. All right, so this first term is what?
0.
0, for two different reasons, actually. It's 0 because the spin is already up. I can't raise it. It's also 0 because I can never satisfy that energy-conserving delta function. We said that the energy of the minus state, this one was the excited state. This had energy plus 1/2. Plus 1/2 h bar omega naught. And the energy of the spin up state was minus 1/2 h bar omega naught. So this delta function inside here is plus 1/2 minus negative 1/2. So this is h bar omega naught plus h bar omega. This delta function is never equal to 0. So this first term is gone for both of those reasons. The second term, however, we're in business for. So I get 2 pi over h bar. Let's pull out the constants. G squared, gamma squared, b squared over 4. S minus, acting on the state plus, lowers it, and I get a factor of h bar squared. And this energy conserving delta function is delta h bar omega minus h bar omega naught minus h bar omega. All right, and I can clean up the expression a little bit. I end up with pi over 2, g squared, gamma squared, b squared. H bar cancels one of the h bars, and I'll use the other one to kill the h bar inside the delta function. Delta of omega naught minus omega. I know that went a little bit fast, but just to recap. We took the rotating magnetic field and we broke it down in terms of two different plane waves, e to the I omega t times some operator, e to the minus I omega t times some operator. We took that and we plugged it into Fermi's golden rule. There were two terms. The first term is 0, both because it can't raise a spin that's already up, and because this one is trying to subtract energy out of the system. The one that came with e to the plus I omega t is taking energy away. And since it's already in the ground state, you can't take energy away from it. But the other term works just fine. I can lower the spin up, and in doing so, I add energy to the system. That is an allowed energy-conserving delta function. So I get a transition rate, and it's no accident that the delta function that I get is a delta function that says the frequency omega of the rotating magnetic field should equal the frequency associated with that energy difference. So this is the resonance condition. Okay, the last thing to comment on this is we know the exact answer. You guys worked it out. The answer in all its generality is there in Shankar. So the exact solution let's see, what we found was that the probability to end up in the state minus, if I compare this with Shankar's 14.4.36, as a function of time. We found the spinner as a function of time. It was Ig gamma b over this omega r sine omega rt over 2 minus I omega t over 2. And if I want the probability, I square it with omega r squared is g squared gamma squared b squared plus omega naught minus omega squared. So if these things are comparable, then I should be able to take the limit of the transition rate and see what I get. So the transition rate is the limit as t goes to infinity, that transition probability divided by time. So I get some constants out front, g squared, gamma squared, b squared over omega r squared. And then I have the limit as t goes to infinity of 1 over t sine squared omega r t over 2. This funny sine squared of t over t is the thing that we said was going to converge to a delta function. We showed that last time, that this is a delta sequence. To get the correct delta function, I need the same argument here and downstairs. So I need to multiply by, I need to bring in this omega r squared. Omega r squared is already there, and I need a factor of 2 to go along with that 2. So I divide by 4, and I multiply by 4. This combination in the limit t going to infinity is pi times the delta function of this argument, omega r over 2, which is 2 pi delta of omega r. So how does it all work out? So this is what we got, r minus plus, coming from first order perturbation theory. The answer we get for the exact solution is r minus plus is, I get a factor of 2, so I get pi over 2, g squared, gamma squared, b squared, and then I have delta function of omega r. Omega r is this square root. G squared, gamma squared, b squared, plus omega naught minus omega squared. They're not exactly the same thing. They have the same prefactor, but they differ by what's inside the delta function. I actually expect them to differ because this is the exact answer, and this one is only good to first order in perturbation theory. So to compare them, I should expand what's inside the delta function. I already have that small perturbation b out front. So to first order, I should ignore any corrections coming from b inside the delta function. If I throw this away, then I get square root of omega naught minus omega squared, which is just delta of omega naught minus omega. So this is approximately equal to pi over 2 g squared, gamma squared, b squared, delta of omega naught minus omega. And we see that the answers agree. So this is another way to think about the paramagnetic resonance problem, that you are starting with something in the ground state, which in this case is the spin aligned with the magnetic field. And that rotating magnetic field is driving in energy, and it is adding angular momentum to flip the spin. And you are allowed to flip the spin when you send in exactly the right amount of energy to flip it. And that is the same as the resonance condition. Okay, so I know all of this came pretty fast, but I wanted to touch on this example of time dependence that you guys have seen before. Any questions?
We went past it a little bit, but I have written down that when we were talking about the perturbed Hamiltonian, we had the S plus and the S minus had a coefficient of e to the I omega t and e to the negative I omega t. But those disappeared when we did Fermi's golden rule.
Yeah, so the e to the plus I omega t and the e to the minus I omega t went into the delta function. So the idea is when you had that, you have some system that has energy levels. In this case, there were 2 energy levels. There was the ground state, which was the spin plus, and there was the excited state that was the spin minus. And there were 2 terms. We had e to the minus I omega t S minus. This e to the minus I omega t corresponds to adding energy in. This is plus h bar omega. That was what made it possible to drive this transition. The other case was e to the plus I omega t S plus. This one actually corresponds to negative energy. If you want to say I'm adding something, it would be adding negative h bar omega. So this one is 0 both because this doesn't have the right angular momentum to transition to a lower spin state like this, and This is trying to take away energy that's not there. So that's why we ended up with two terms in Fermi's golden rule, one coming from the adding energy with this operator, a different one coming from subtracting energy with that operator. Does that make sense?
Yes, it does.
Okay. Yeah, so in general, if you have a finite sum over various plane waves, each one of them can drive a different transition. You could have either the minus I omega t and either the minus 2 omega t. Each one would be trying to add h bar omega or 2h bar omega to the system in that case. All right, any other questions? So seeing as how it's already almost 10 minutes until the stop of class, we're not going to get very far into a discussion of interactions of atoms with external magnetic and electric fields. Let's give it a shot anyway and see how far we get, and then we'll continue with it on Wednesday. So the point of this discussion, where we're ultimately aiming for, although I guess we probably won't get there until next week, the goal is to describe the photoelectric effect in time-dependent perturbation theory. Time-dependent perturbation theory. So how does that fit within this picture? It's actually not so different from this example that we just did. We're going to start off with a system with energy levels En in the hydrogen atom. There's going to be the ground state with energy E naught. This is, say, the N equals 1 level. There's the excited state, N equals 2, with energy E naught divided by 4. And there were actually 4 of these, right? 1, 2, 3, even excluding spin. There was the 2s and the 2p states. There were 3 of the different 2p states corresponding to the 3 different values of Lz. And then there was the third excited state, N equals 3. And then in that case, there were 9 of them. N equals 3. We had the 3s, the 3p, and the 3d states. There was 1 3s, there were 3 3p's, and there were 5 3d's corresponding to the different values of angular momentum. So given this atomic structure, how can I drive a transition by sending in an external electromagnetic wave? So if we send in an electromagnetic wave, which has both electric and magnetic fields, this is E of t, and perpendicular to that, I have B of t. These things come in like sine and cosine waves, exactly like this example from paramagnetic resonance. So we'll end up with something like E of t, the electric field, is some constant direction, E naught, times cosine omega t. And I'll end up with a magnetic field, B of t, which is some B naught, which is related to E naught, times cosine omega t. And these things we said can be written as 1/2 E naught e to the I omega t plus e to the minus I omega t. And 1/2 B naught e to the I omega t plus e to the minus I omega t. So we can use this kind of formalism with Fermi's golden rule to calculate the transition rate from, say, the ground state. And if I send in electromagnetic waves with exactly the right frequency, tuned to this transition, let's say, then I can absorb energy h bar omega corresponding to this energy difference and drive a transition from the ground state to the first excited state. Or I can drive a transition all the way up to positive energies into the continuum where I free the electron and make it a liberated plane wave with some positive energy that can escape to infinity. We have all of the machinery to do that, but we need to spend some time discussing what is the response of the atom to an external electric and magnetic field. And before we tackle the time-dependent case with all of these extra complications, which is very cool and beautiful, we should review what the results are for the static case. So first, response of the atom to external static electromagnetic fields. So some of these things I'm sure you will have seen in your undergrad quantum mechanics. The response to the external magnetic field is called the Zeeman effect. And we've already discussed spin and magnetic fields to death so far this semester. We already know that the orbital angular momentum will have an alignment energy with the magnetic field. The spin angular momentum will also have an alignment energy with the magnetic field. So the Zeeman effect couples to the Z component, let's say, of angular momentum Lz, and also the Z component of spin angular momentum Sz. The picture can get more complicated when you start to factor in things like the fine structure splitting, which has L.S coupling. We're not going to worry about that for this discussion. The coupling to the external electric field is called the Stark effect. And in my head, I don't know whether to think Game of Thrones or Marvel when I discuss this. In this case, the Stark effect is referring to the coupling of the electric field to the intrinsic dipole moment, the electric dipole moment of the system. So in this case, our Hamiltonian will be something like E times the electric field E times the position operator R. So this couples to electric dipole moments. So the Stark effect is actually significantly more complicated than the Zeeman effect because of its dependence on the spatial position variable. All right, what do I have time to go through in 5 minutes? Maybe the Zeeman effect. So we know very well what the response of atomic degrees of freedom to an external magnetic field is going to be. If the magnetic field is B equals B times the unit vector K along the Z-axis, then my Hamiltonian is the Coulomb potential, and the extra interaction is minus mu dot B for angular momentum L, and another minus mu dot B for the spin angular momentum S. It looks redundant to write it twice, but I'm doing that intentionally because they come in with different coefficients. The orbital angular momentum comes in with minus gamma, which is minus E over 2mc Lz times the magnetic field B. The spin angular momentum, however, has a G factor in front. G equals 2 or thereabouts. Minus E over 2mc times the spin operator Sz times the magnitude of the magnetic field. So when I combine these two things together, the actual Zeeman splitting in the magnetic field depends on a combination of the two with unequal weights because of that G factor. I have Lz plus G times Sz. And that G factor is approximately 2 for the electron. So if I ask, what is the first order correction? That is the first order Zeeman shift in time-independent perturbation theory. That is the first order shift E1 in any atomic state. So let's say in NLM, I guess it's not going to depend on most of those things. It's going to depend on Lz and Sz. So I need to calculate the expectation value of a state that has a given Lz and a given Sz of the perturbation EB over 2mc Lz plus GSZ in the same state. So I get a factor of h bar e h bar over 2mc times the magnetic field, and the quantum numbers are Lz plus g sz. This combination of coefficients is just the Bohr magneton. So let me call this E1 Zeeman. All right, this is the first order Zeeman shift. There are caveats associated with this. I've been talking about L and S in a product basis. That's fine for the Coulomb potential, but it breaks down when we include the fine structure with L dot S coupling. So this assumes that the energy level of the splitting, mu b times b, is large compared to the fine structure. So parametrically, this means that this energy splitting compared to the ground state energy needs to be much greater than alpha ENM, which was the parameter controlling the size of the fine structure corrections. All right, so what does this do? It gives me an interesting mixing of the different spin and angular momentum quantum numbers in an external magnetic field. So let me just discuss the splitting of the first two levels. So I started off with the ground state, energy E naught, and there were two levels there, including spin. This is the 1s state, and I had Lz equals 0 and Sz can equal plus or minus 1/2. So under the influence of the magnetic field, I have two combinations. So Lz is equal to 0 in the S wave state. And so I just have plus or minus 1 if G is equal to 2 and the spin is always plus or minus 1/2. The result is that one of these levels goes up, one of these levels goes down. Relative to that original energy, I have a shift plus mu dB and minus mu dB. The state that goes up in energy is the state Lz equals 0, 2Sz equals plus 1. The state that goes down is Lz equals 0, 2Sz equals minus 1. So for the ground state, there is no orbital angular momentum. It's just the spin, which is coupling to the external magnetic field. At n equals 2, however, the situation is significantly more complicated. So we have energy E naught divided by 4. We had the two S levels, and there were two of them. The two S levels will split in exactly the same way. Plus mu BB minus mu BB. In the 2s levels, we had Lz equals 0, Sz equals plus minus 1/2. So the state that goes up is Lz equals 0, 2Sz equals plus 1. The state that goes down is Lz equals 0, 2Sz equals minus 1. However, there are also the 2p states. These are the two p states that have Lz equal to plus 1, 0 or minus 1, and Sz equal to plus minus 1/2. So I've got to look at how many different combinations I can make of this type. The biggest number that I can make is Lz equals plus 1, and 2Sz also equals plus 1. So I've got one splitting that goes up by 2 mu b. This is the state Lz equals plus 1. Two Sz also equals plus 1. I can have a state where Lz is equal to 0 and the spin is equal to plus 1. So I can have a splitting which is, sorry, this was plus 2 mu BB, this is plus 1 mu BB. So this is the state LZ equals 0, 2SZ equals plus 1. Likewise, I've got the opposite of these guys. Minus mu BB corresponding to LZ equals 0, 2SZ equals minus 1, and minus 2 mu BB LZ equals minus 1, 2SZ equals minus 1, and I can get 0 from either of the other two combinations. I can have LZ plus 1 spin minus 1, or I can have LZ minus 1 spin plus 1. So I also have an unshifted state, two of them, that correspond to LZ equal plus or minus 1, 2SZ equals minus or plus 1, so that the total adds up to 0. And you can see that the structure is just going to become more and more complicated the higher up you go in N. I'm going to generate more and more pieces of angular momentum, which is going to give me more and more splittings of the atoms. So the effect of the magnetic field is to take previously degenerate states and split them based on a combination of LZ and SZ. The splitting is proportional to the magnetic field. So if the field is weak, I split the lines a little bit. If the field is strong, I split them a lot. And I can extract information about the amount of angular momentum present by looking at the dependence on the magnetic field and seeing those splittings. Okay, I think this is all that I wanted to say about the Zeeman effect. Next time we will discuss the Stark effect, and that will bring in lots of our previous discussions about angular momentum and parity. And then I don't think we're going to get very close to the photoelectric effect on Wednesday, so we will probably continue that on Monday. Any questions?
Thank you.
Thank you guys very much.
Dr. Sievert?
Yes, sir. Oh, yeah, I got your email, Jeremy. I need to respond to you. Do you have a preference?
I don't care. I was just making sure what was the plan.
It was a good question. It hadn't crossed my mind before. Maybe I'll send an email and ask what everybody's doing. If people are going to be out of town, then maybe we'll just cancel.
Okay, sounds good.
All right,
Thank
thanks.
you.